Okay, this video goes with the worksheet entitled Independent and Dependent Events. Now, a lot of the formulas for these compound events, probabilities, is the same as what we talked about for mutually exclusive events. So you'll see me kind of touch on those kind of quickly, but the main thing we want to do is start off talking about what makes two events independent versus dependent. Now, the first thing you need to realize, when you talk about independent, we're talking about things that stand alone. Okay. Now we're talking about compound events again. So we're going to perform at least two events, and we're going to look at their combinations, the probability of this combined event happening. So we can still have an and sort of situation where we multiply, an or situation where we add, and even a conditional probability. Okay, so let's look at an example of when you have independent events. So I have I guess I'll use a deck of cards again. Okay, so without jokers, I know that there are 52 cards in a deck of cards. Okay, there are 4 different suits. The hearts, clubs, diamonds, spades. And when you go ace through king, there are 13 cards in each suit. That's what makes up the 52 cards. Now, let's say, for example, I want to find the probability of drawing 2 hearts out of this. Okay, so the probability of the first heart number 1, and the probability of the second heart number 2. Okay, now one of the things they talk about when we talk about independent events is the idea of replacement. Okay, so let's say we want to look at what's the probability of this first event happening. Well, the probability of drawing a heart, since there are 13 of them, would be 13 out of 54, or 52, sorry, which is 1 out of 4. So I got a 1 out of 4 shot of grabbing a card, and having it be a heart. Now, if I leave that card out and do not replace it, then the number of hearts that are left, assuming the first one was a heart, is now 12. And the number of cards left to choose from is 51. So without replacement, we end up with 2 different probabilities. And so the probability of drawing both heart 1 and heart 2 is 1/4 times 12 over 51. Okay? So if you don't replace, then the first event alters the second event. That makes them dependent. So the second one is dependent upon the first one and what happens. Okay? So let's say, for example, then I take and plug it back. I do replace it. So I'm going to say this is without replacement. So probability of heart 1 is still 1 out of 4. When I plug it back in, it still means I now have 13 still available, because I might choose the same card again, okay, coincidentally. And then I have 52, so the probability stays the same, okay? So that's how you determine whether they're independent or dependent. Does the first one affect the second? Okay, and like I said, the key word that you'll see in several of the problems on that front side is the idea of replacement. Okay, so with replacement, we can say independent. Okay, without replacement, we would say dependent. Okay, so so that's the first part of this, and we'll look at some of the exercises there, and then we'll review some of the formulas, and then talk about the second page as well on the back side. So on questions 1 through 4, questions 1 through 4 says determine whether the scenario involves independent or dependent events. Okay, so number 2 says a bag contains 8 red marbles and 4 blue. You're going to randomly pick a marble and then set it down, and then you're going to pick a second marble without returning the first back to the bag. What's the probability that the first marble is red and the second marble is blue? Okay, well, the key there is without returning means there is no replacement. Okay, and no replacement allows me to say that on number 2, question number 2, these are dependent events. Okay, dependent events. Okay, again, if the second event is not affected by the first, okay, then we're independent. Okay. Now, number 4, similar situation. You have a cooler, contains 10 bottles of sports drinks. 4 are lemon lime, 3 orange flavored, 3 are fruit punch flavored. 3 times we're going to choose a drink, okay, basically look at it, return it to the cooler, grab another one, look at it, return it to the cooler, okay, and then do that a third time as well. Okay, and we want to know what's the probability. The first time we get lemon lime, the second, third times we get fruit punch. Okay, every time that we return the bottle to the cooler, okay, we end up with the same probability of choosing that or a different one. So in this case, because they all go back to the same possible chance of choosing, like the first time originally was, okay, on number 4, we would say these are independent events. Okay, so that's the difference. That's what they're asking you to do there. Okay, now we're going to actually apply that and find some probabilities then for problems 5 through 8. Now, again, what we want to look for here is this an and situation, which is typically what they are when you do successive events, or is it an or situation? Okay. Number 7. It says there are 8 shirts in your closet. 4 are blue, 4 are green. You randomly select one to wear on Monday and then a different one to wear on Tuesday. Okay. You wear blue shirts both days. Okay. what's the probability of doing that? Okay. Now, one of the things about these dependent events is we've got to assume that the first event happens when we calculate the second. So in this possibility here, okay, of 8 shirts, we know that for the first day, if I get a blue one, the probability of blue on the first day is 4 out of 8. Okay. Now that shirt's going in the laundry. Okay. And so I look at my closet the second day and I'm trying to find the probability of blue on the second day. There's only 3 left to choose from out of 7 total shirts. Okay. So these are 2 independent events. And I want to know what's the probability that both of them happen. So this is an and situation. And when they want to know and, okay, you multiply. So this is the probability of blue and blue. If you want to call it B1, blue day 1, blue day 2, then that's 4 out of 8 times 3 out of 7. So 12 out of 56, which is 3 out of 28 when you reduce it down. Okay? Now, if, for example, if they do replace, then we go back to the original probability the second time. Okay? So let's say we've got number 8. A basket contains 5 apples and 7 peaches. So here's my basket. 12 items. Okay? 5 apples, 7 peaches. Okay, you randomly select one piece of fruit and eat it. Then you randomly select another piece of fruit. The first is an apple, the second is a peach. Now, obviously, since you're eating the first piece, you can't replace it. Okay, so this is just like number 7. Okay, this is an example where we're doing an and. Okay, but be careful what we're looking at here. Okay, so the first time is an apple. There are 5 apples. So the probability of choosing that apple on the first attempt is 5 out of 12. Okay, now the probability of getting the peach on the second attempt, okay, there are 7 peaches, but there are only 11 pieces to choose from. So in this example, when I multiply, this is going to be 5 over 12 times 7 over 11, which is 35 over, I think it's 121. 132, sorry. So this would be 132. Okay. So again, when there's effect on the numbers, we have to take that into an account. Okay. So next page. I seem to have misplaced the next page. So give me just a minute. Thirteen through, well, I guess 9 through 12 first. Maybe I better talk about one of those first. Okay. Now, on problems 9 through 12, okay, you simply got to ask yourself, careful about the wording, okay, what the probability of not A is 3/4. Okay, the probability of B is 3/10. The probability of A and B is 3/40. Okay, are those independent? Okay, well, let's look at it this way. The fact that they use a complement again is part of my problem. So if I know the probability of not A, is 3/4, then the probability of A actually happening is 1/4. Okay, 3/4, 1/4, they add to 1, okay, when they're true complements like that. Now, here's the other part of that. I need to know that the probability of A times the probability of B equals the probability of A and B. Okay, that is what we're trying to test. So probability of A is 1/4. Probability of B is 3/10. Multiplying those together, well, probability of A and B is given to be 3/40. And I want to know, when I filled in, are those two sides equal? Yes, they are. Okay, so when you finish that problem out, it looks like that. So since the two sides are equal, then we can say that the two events are independent. Okay, so 9 through 12 looks like that. That's what they're asking you to do. Okay. On 13 through 18, okay, the numbers get a little bit harder to work with. The process is the same. They do have some conditional probability to deal with here. So let's play around, probably adding one of those. If it's and, again, it's a multiplication problem. Okay, so number 15, I see an and. Okay, let's try number 14. Okay, I know the probability of B okay, the probability of B is 9/20. The probability of A divided by B is 1/5. What's the probability of A? Okay, so we know, formula says the probability of A given B equals the probability of A and B over the probability of B. Okay, so that's the formula for conditional probability, which is what we're dealing with here. Now I'm going to fill in the pieces. A over B, the probability given is 1/5. Probability of A and B, I do not know. But the probability of B is given to be 9/20. Okay? So I need to solve that for A and B. So to get rid of that fraction in the bottom, I'm going to multiply by 9/20 so that those drop out. And this becomes 9/100 equals the probability of A and B. Okay? Well, because this is an independent event, then this, A and B is the same thing as A times B. And I said it before, B is 9/20. Okay, so B is 9 over 20. So I'm going to sub that in again. And now to solve this, I need to multiply both sides by 20 over 9. So the 9's cancel out. Actually, these fractions cancel out. So we're left with the probability of A is 20 goes into 105 times. So all that's left is 1/5. Okay. Now I'm trying to think if that will always be true, because notice that's the same as what's given as your conditional. I'm not sure if that's always going to be true or not. I'm thinking it probably will be, but this is what you will do. That's the idea, the formula you're plugging into as you go through and perform those. Okay, so 13 will be similar, except you're plugging in. You know, if you look at that one just real quickly, okay, again, to find probability of B given A, okay, I want to find the probability of both of them, A and B. And this time, the second value given is A. You always divide by what this letter after the line is. So multiplying the two probabilities together, you get one, that's 1/4 times 3/5. Okay, dividing by the 1/4, and you're left with 3/5. Okay, so that's kind of how those are going to be worked with. Number 17 has got to not be. You have an OR situation on 18. Remember, that just means you're adding. So number 18, if I help you set that one up. Okay. The probability of A or B equals the probability of A plus the probability of B. And since these are independent events, there's nothing to subtract off. So all you're going to do is you're trying to find, well, you're given this, given the OR. This is 7 over 10. And you're trying to find B. And this would be one of those situations where I would use my calculator, type in the fractions. Sorry. Get up here where you can see. Okay. So I would take this, all that's left over here is what I'm trying to find. So if you type this into your calculator and change it back to a fraction, okay, you should be able to find what you get out of that one. Okay, so let's try that real quick. So parenthesis 173 divided by 200, parenthesis divided by, or excuse me, go backwards, minus, okay, parenthesis 7 divided by 10, parenthesis, enter. So you get that decimal point 165. I'm going to go back to my math button, use the fraction key, and change that back. And it looks like 33 over 200 is my answer. Okay. Moving down the page, 19 through 22. You have a conditional probability on 19, Just fill into the formula. 20 is an and. 21 is conditional. 22 is, you have a couple things there. You have an or, you have a conditional as well. So I'm going to treat this like the or situation. I think I can do that. Okay, we'll test it and see what they have. So again, probability of A or B equals the probability of A plus the probability of B. So A or B is 0.72. Probability of B is 0.45. Subtract over the 0.45. I get the probability of A to be 0.27. Which is not what they get for an answer. So let me see if there what else they have hidden in this problem. Okay, so let's say that I get that. So probability E given A. So okay, this isn't how they intended this problem, but there's some missing information there, and so what I've got is we're going to call good. So again, let me just run through what I did on this one. Okay, so the probability of B is given to be 0.45. The probability of A or B is given to be 0.72. What I did is I chose to call these independent events with no overlap, and I didn't even look at this part here with the conditional probability. I know it should probably be considered, but I'm not sure what their intent is. So here's what I did. A or B equals probability of A plus B. They gave us the A or B is 0.72. B is 0.45. I subtracted that over, and I got the probability of A to be 0.27. Okay, so for the purpose of your homework, again, this won't affect, this is a much more difficult question. This won't affect the other ones. Do them as we did in the ones that examples I gave you. But we're going to leave that answer as that. Okay, so If you have any more concerns, just email me with the problem numbers, and I can always write up more solutions and send you some answers on some of these things. So, you know, I'm hoping you guys are doing okay on these. I'm not hearing a lot of information coming back from you. I've got some worksheets that have come in, and hopefully that's going to be enough just to get us through in the days we have remaining. So, thanks.